Harsh. Hi, Anshu. How are you guys?
Good. How are you?
Very good.
All right. Hey, Puneet. Good to see you.
Harsh, Anshu.
Hi,
Hello.
So as people are joining, Vineet, one of the things we do, one of the agendas of this meeting is to learn more about the speakers. More than the talk, I find that more interesting. So we know you from my IIT days. I mean, we know you those 4 years. So while people are joining, maybe you can start and tell us a little bit more about your journey before that. I mean, from your childhood to the moment you heard that you were number one in JEE. And then
same as everybody else's journey. Nothing very spectacular about it.
Where did you
See,
grow
Vineet,
up?
this is so typical of you, Vineet, right? You're like, okay, nothing spectacular.
हाँ मतलब देखो स्कूल जाते थे अपना पढ़ाई करते थे सब लोगों की तरह nothing very different.
और लोग पढ़ाई नहीं करते थे मुझे ऐसा लग रहा है.
All right, so something that will be different. Let's say, I mean, what about your journey after IIT? We lost touch after IIT. What journey did you take from
After IIT
to here?
हाँ बहुत सारे लोगों की तरह I came to the US also to do a PhD. And then I worked at a bunch of companies. I started at Google about 18 years ago. And I was in India for 5 years. So I met a lot of you there.
Yeah, how was your stint at NASA? There was some discussion about it when Perseverance landed on Mars.
अच्छा था. Actually, I was working on rovers in NASA, on modeling rovers. But I was there only for about 2.5 years. फिर हमारी सारी टीम ही छोड़ के चली गई. So
oh no. not got to Mars, luckily.
नहीं बस they all went to various other companies and all, and so जो मैनेजर था वो तो MIT में prof बन गया और वो अभी भी वहीं पर है.
Yeah. So hey, we can say something. Can you hear me?
Yes. Yeah.
Yes, we can hear you.
Yeah. So no.
That's fine.
So sorry, I joined a little late. So क्या हो गया? But Vineet Gupta is Hall 2 guy. So yeah, Hall 2.
You need to grow up, Rohit.
I don't want to grow up. Who wants to grow up? Right, Hall 2 ka tempo high.
Yeah, Hall 2, like we are already grown up. Like so all three guys need to grow up.
Rohit is
Okay, so basically what I want.
Rohit is trying to provoke a reaction because Amit is not there, but I can see Anshu on the call, so we'll hold our horses.
No. I don't want to provoke any reaction because there is nothing. All people tempo high here. No reaction needed, right? Right. So no. What I say is that what we need. You were in Hall 2 with me, of course, and then of course several of us, and then I mean you have been a very humble guy all along, and then what I want to say was that. उस समय हम लोग को of course when we were in the students days then we all didn't get a chance to interact with each other too much, but of course I got a chance to see you at Google, right? So you and Sriram, you welcomed the faculty from Cornell.
ये minimum class size का wait हो रहा है क्या?
So can you guys hear me or no?
Yes. Yes.
Yes. So I want to say is that so I'll just give an example, and then I want to say the point is that all of us had something unique to offer, but Vineet and then Sriram basically they welcomed Cornell faculty at Google, and then they told us कि academia में क्या होता है, but this is what the real world in the IT industry and the technology industry is all about. And then they were so humble and they were so welcoming. So I just want to say that thank you very much for basically, building on the ITK 89 network and then building all of us here. And then, of course, this is a great opportunity for all of us to hear what we are doing. So thank you. That's it.
Okay, great. Hey, by the way, Rohit, you also visited us. You forgot.
Yes, indeed, right. So, Vishwa, when you do the talk, then I'll do the same thing for you. Yes, because Vishwa did the amazing thing too, but he welcomed Cornell faculty as well, and then it was amazing.
No, it was great. You visited. So Vineet, coming back to the topic. So
yes, let's go to Vineet. Okay.
So one other thing I would ask, then we can start on the actual presentation. So while you were at IIT, I mean, what are the couple of things you remember? Somebody who actually impressed you, either as a faculty or even a student who impressed you. It'll be interesting to hear from you.
Well, actually, everybody was pretty impressive, but I'm more impressed with how people have done after IIT, which is actually quite amazing to see, like all the amazing accomplishments of people. Like, I mean, Sanjay is here and obviously the most accomplished person of our batch.
No, I mean, overall, it was very clear. I mean, if you gate it in a way that only smart people come in, I mean, it's a given that they will do well.
Yeah, but still, it's a lot of fun to see what all people have been able to do.
But while you were there, what impressed you? Who impressed you?
Well, I think the most impressive person in the whole batch was clearly Shirish. I think there's no doubt about that. But there were lots of other people who were doing very, very cool things.
Perfect. So, okay, the floor is all yours. Educate us, man.
So I would like this to be a very interactive session, right? And so everybody should just interrupt at any point of time, right? There is no, I don't have a particular place that I want to get to. So we'll just go on for as long as we feel. And please ask lots of questions.
Yeah, that's perfect. That's the idea of these webinars. There is no formality here. There is no hidden agendas or anything like that. It's just a chat between friends.
Right. And in fact, now we have a lot of people, probably more than in ESCO 1 at 8 o'clock in Kanpur. So I will start this.
So I mean, just so you know, a couple of days back there was a huge discussion on would it make a difference if the faculty had more industry experience, because Modi has proposed this and IIT Delhi has already adopted this, and there was a good back and forth on this. So this talk lines up quite nicely with that. Imagine you are a faculty member with some industry experience, and then we are again in Math 101.
Yeah, so this talk is actually a very interesting merge of industry and engineering and mathematics, and I'll probably come to that. But anyway,
just a quick interruption, Vineet, just for a moment. Sandeep, are we going to record this? Are these sessions recorded? I think it will benefit those who are not able to attend today.
Yeah, I don't know if Sandeep is here on the other one, but they're all recorded. You go to the same link. All the previous recordings are also available. So if you want to look at Sanjay's talk, for example, or Rohit's talk, any talk, they're all there.
Perfect. Then sorry about the interruption. Please continue, Vineet.
Yeah, no problem.
Okay, so let's get started. So Vishwa just asked me to talk a little bit about the kind of work that I do. And I work on machine learning, which has become a really hot topic these days. But so I just wanted to peek a little bit behind the curtain and show you a little bit more about what machine learning is like. And clearly, there are many ways of looking at machine learning. I'll present you my perspective, and other people can then share what they feel machine learning is like. So my perspective on machine learning is more around the lines of optimization. So that's what I will talk about today. So I will talk a little bit about the optimization problem, and then I'll talk about adaptive optimizers, which are a particular kind of optimizers for machine learning. And then I'll talk about, if we have time, we can talk about a couple of optimizers that I've been working on over the last 2-3 years. So let's start with what is the learning in machine learning, right? So this can be answered in a very simple way. This is what machine learning tries to do. It tries to find the best function from a class of functions. Now, this is a very abstract definition, and let's dig a little bit deeper. So first of all, let's talk about what does it mean to have a class of functions. So remember when you were in your first year and we used to draw all these graphs, right? You would plot some points on a graph and then draw a straight line between them, right? So here the class of functions were straight lines, and we wanted to try and find the best straight line that fit all of our points, right? And in fact, the class could be specified by just 2 parameters of the line, that is the slope and the y-intercept, right? Y is equal to mx plus b. So similarly, for other kinds of problems, there are different classes of functions that we want to find the best function out of. And classes can be specified in many different ways. And in fact, the problem of choosing the class is a very difficult problem, which I will not be getting into very much in this talk. But if you choose a class that is very big, then it might be very difficult to find the best function. On the other hand, if your class is very small, then the best function won't be very good, right? So there is this, sorry, is there somebody trying to speak? Okay, so this the class is a very difficult topic, how to determine the correct class for the problem. And a lot of effort in machine learning is actually spent in trying to come up with the correct class. So very often the class of functions is going to be specified as a set of parameterized functions. What do I mean by that? Just like in a straight line, you have 2 parameters, the slope and the intercept. In a typical class, you will say that all that my functions that I want to determine are going to be specified by a bunch of parameters, right? So once I specify all the parameters, in the case of the line, slope and intercept, then I have completely determined my function. And now, of course, I can feed the function an input and it will produce an output or the prediction, right? So in today's modern machine learning, most often the class of functions is specified by a neural network. And let me, for those of you who are not familiar with neural networks, I'll give you a little crash course in 2 minutes. What is a neural network? So a neural network is again a representation of a function. It takes a bunch of inputs, the x1, x2, x3, x4. It's a vector of inputs, and out comes a vector of outputs. So for example, if you want to use your neural network for, say, classification of emails into spam and not spam, you first take your email, convert it into a vector of numbers, feed into your network, and out will come a classification yes or no. And similarly, you can do machine translation, or you can do predictions of all kinds, right? In Google, for example, we use neural networks to predict whether a user is likely to click on an ad or not. All of these can be specified by abstractly by just considering the input as a set of numbers, and the output is whatever you want it to be, also a set of numbers. And the way neural networks work is pretty simple. So here, so neural networks, by the way, as Sandy was pointing out to me just before the talk, they're very old technology. They were invented in the 1940s. And in fact, he pointed out that there was a class in IIT which was discussing neural networks and the related algorithms. So a neural network is a very simple object. All it does is it starts off with the input layer. This is the green stuff at the bottom, which is just a vector of numbers. And then each layer is computed from the previous layer And of course, I'm simplifying a little bit, but not too much. So each layer is computed from the previous layer. So you take the previous layer as a vector, you multiply it by a matrix. I hope all of you remember some linear algebra. And you get out another vector. And now the only thing that is special about neural networks is that you apply a simple nonlinear function to each element of the vector that you get. Most of the time,
can I ask
yes,
a question or no?
absolutely. Please do ask questions.
Yeah. Hi, Vineet. This is Rohit again.
Yeah.
So I have one very quick question, maybe a naive one, but I think you can probably answer it for everybody.
Yes.
I think it's one of the basic assumptions of the neural network. But here's my question. So let's say something happens, right? Something happens, which means that somebody makes a choice or decision, whatever, it will get captured by the neural network, right?
Right.
And then the algorithm will take care of it and then basically make decisions. Just exactly what you said.
Yeah.
But let's say somebody chooses not to do so, right? So there are a lot of people who choose not to do something. And then that something could be anything. Something could be, I don't want to choose to buy this product. I don't want to go here, whatever that may be.
Right.
But basically, in terms of algorithm, that means it's a zero.
Not
right?
necessarily.
Right,
Because-
right. So just to let's be complete, because I wanted to hear your thought. So
Yeah.
there could be many reasons why people choose not to choose.
Right.
And then how does your algorithm take care of that? Because that is a big point. I think in many many points of the life is that basically people are saying, okay, what if we do not choose something? How does the predictive algorithms, like what you are saying, take care of it? So just think about it,
Yeah.
and then please address it some time in your talk. Not right.
Yeah.
Okay.
Yeah. So
Thank
yeah,
you.
we can talk about it very soon, actually.
Okay,
But let
thank
me
you.
The neural net presentation. So this function that I talked about, this nonlinear function can be extremely simple. For example, the most common function that is used today is that if the answer is negative, just make it 0. Otherwise, whatever was given, let that be the answer. So it's if the function is x if x is positive, 0 if x is negative. So it's a very, very simple function. It is applied to each value, and that gives you your next layer. And now you keep doing this one after the other until you reach the final layer, which is the answer. So this is a very simple neural network, but it is very effective. And in fact, we use this in several of our Google systems all the time. Right. And clearly a lot of work has been done on these, like what kinds of matrices should we allow here. The W's are the matrices, by the way. Right. And in fact, now you can see that the class is specified by the various W's. Once you specify all the W's, everything is done. Right. So the different W's represent the different functions that the neural network can learn. And the set of all possible matrices determines your class. So the person who is designing the neural network, their main job is to determine how many, what are the dimensions of each of the matrices inside, and what is the dimension of the, how do the connections happen? Like maybe you don't want everything to be connected to everything, so you want your W to have some specific form, and so on, right? But those are all details that we don't really need to worry about. And in fact, in my talk, I won't use neural networks at all. I just wanted to provide a very brief idea of what is a neural network for people who may have heard that term but are not familiar with it.
Vineet, what defines the number of layers? How do you know there's 2 or 5?
Yeah, so it can be anything. So this is dependent upon the person who is trying to solve the problem. So this is basically, this comes down to selecting the class that you want to learn over. If your class has many layers, if your network has many layers, it is one kind of class. Otherwise, you can have a very shallow network that's a different class of functions. And this is now you have to use some of your intuition behind what your problem is. You can also try to experiment, and people are doing that. There is also an effort in Google to try and learn the number of layers and the number of units in each layer automatically. So that's a problem that we don't have. That's like sort of almost like an art.
Thanks.
Hey, Vineet, this is Rajiv. So
Yeah.
where is the? So you alluded to some non-linearity. Where is
Yeah.
that?
So that sigma function is the nonlinear function. It's a very simple function.
Okay.
Most of the time, it is just like a function that says 0 if x is negative and x if x is positive.
Got it.
Right? So it's a very simple nonlinear function. The power of neural networks comes because the number of units can be very large. So like each layer can have thousands of units. And so now you can see that if you're going from a layer with say 1,000 units to a layer which has 2,000 units, you have a matrix of size 2,000 by 1,000. Right? So that's 2 million parameters that you get to learn. And that's actually not a very large number. These days, people have neural networks with billions of parameters even. Right? So in fact, the latest neural networks that are coming out of OpenAI have 175 billion parameters in the matrices. So the number of parameters, by the way, is simply the total of the number of matrices, the total number of elements in all these matrices. So when you see somebody saying my network has 1 billion parameters, that means that the total number of numbers in all the matrices is 1 billion. Right? So there's nothing sort of very complicated or magical about these. Right?
One quick question,
Yeah.
Avinash here. Can you give a practical example of a layer? For example, if I'm trying to solve a problem of somebody buying from Amazon, is layer like the customer attributes or the prices? In that kind of example, what are the layers?
So layers are just abstract things. Layers are exactly what I've written here. The input layer, of course, is determined from your input. Like somebody is trying to buy something. So the person's attributes written out as a vector. The attributes of the product also written out as a vector. So the person's attributes can be their like their age, their gender, where they're at, and so on. And it's up to the person who's doing the modeling to convert each of these into a number. For example, let's say your age, right? You can represent your age as a 100-dimensional vector with a 1 in the place where whatever age you are and zeros elsewhere, right? So that's how you can convert your age into a vector. Similarly, you can convert the page into a vector. You can look at all the words and you can just have a large dictionary, and you can have a 1 in the place where the word is and zeros elsewhere. And that is now a representation of a word. You add up all the representations of the word on a page, that's your representation of a page, and so on. Right? So
Vineet,
yeah.
This is Harsh. So being a mechanical engineer, it always gets back to mechanics. But this often reminds me of finite element analysis in the physical domain. I mean, we do about the same thing, isn't it?
I think there is a connection, but I'm not sure. So I don't know very much about finite element analysis. I don't know only the very bare minimum. So in a sense, what you're doing is, you're passing information at one end and it's sort of being propagated and it comes out at the other end.
Exactly.
Which is what happens
at each node. All right, please go ahead.
Yeah. So Avinash, to answer your question, the internal layers sort of don't necessarily have a meaning, right? They're just numbers. You feed it something that has meaning to you. The internal layers don't have any meaning, but the output layer will have a meaning. Now, of course, the idea behind the internal layers is that they're trying to be higher level features. For example, if x1 through x4 are the pixels in your image, then you hope that the internal layers are representing, lines in images or objects in images. Like, is there a car in this image or not? But we don't really have a good understanding of what the internal layers are like.
So Vineet, I mean, one of the challenges that it poses is that how do you explain, the explainable part of AI?
Yes, and that's a big problem. I'm not going to get into today, but it's a huge problem. And neural networks in particular are very bad at this. they're really bad because right now there are efforts, by the way, there are very good efforts in trying to explain neural networks, but just looking at the function that is computed, it's not going to be very helpful.
Yeah, because it's leading to weird problems like bias in AI.
That is true. And by the way, bias in AI is already comes from the bias in I, right?
Yeah, for sure.
So neural networks typically reflect what is given to them, and so they are not in themselves biased, right? In fact, they may be less biased than the people who are trying to build the neural networks.
Yeah. I mean, it depends on the data, garbage in, garbage out, I guess.
Right. So,
Vineet, this is Sanjay.
Hi.
Hey, quick question. So when we talk about these layers, and when we say neural network A is better than neural network B, so then are we saying that's not the mathematics, but the intuition of the person designing the neural network, or intelligence of the person designing the neural network that's why one neural network is better than the other outside of mathematics?
So in fact, let's come to that question right away. So remember, so I just already defined from my definition what is the class of functions, and I hope that's sort of clear now. But what do I mean by best? And that is directly related to the question you just asked. What does it mean for one neural network to be better than another, or what does it mean to be one function to be better than another? So here the answer is, we are designing these neural networks or these machine learning systems to solve a particular problem. And whatever function solves that problem better is the best function. For example, if we are trying to design a network to classify spam versus not spam in email, then the better network is the one that gets that right more often, right? It classifies spam as spam and not spam as not spam, right? So now, how do we tell the neural network? How do we distinguish between networks? So here is where we go into the data, right? And this is the other big thing about machine learning. Machine learning depends upon lots of data. So how do we train? How do we sort of find the best function? Well, the way we do it is as follows. We start with a bunch of examples, right? So in this particular scenario, we will start with a bunch of examples like, here is the input and this is the output we would like to see. For example, in the case that Avinash was pointing, we have a bunch of users and pages, and the output is we want to predict whether the user is going to buy the item or not, right? So we have a large number of examples, and you can see these days with the internet, the data is like sort of in plenty. So now what our definition of best can be narrowed down. And the definition is, we want to find the set of parameters W, which will determine our function. And we want the function that is going to be as close as possible to the expected answer for all the examples that we gave it. Does that make sense?
But Vineet, I mean, does it also mean that, I mean, you want to find such a class with the least number of weights?
Well, that is a separate problem. And yes, it is important to do that, but for a different reason. So of course, the way I have stated this problem, you want to just be able to predict the answer for the examples that were given. But of course, that's not the most interesting part, right? Of course, for those examples, you already know the answer. You want the neural network to be able to predict the answer for other examples that you don't know the answer to. And that's a problem called generalization. Some of you might have heard that term, right? So, so now this is where the choosing the class comes in. So if your class is chosen very carelessly, for example, let's say you choose your class to be all possible mathematical functions, then clearly the best function for that is for xi, predict yi. I don't care about anything else, right? You can memorize your xi's and yi's, right? So for x1, you memorize that I must say y1. So it's like, in a test, if your teacher already tells you that, hey, these are the 5 questions that will come on the test, you don't need to understand how to work what is the proper way of doing the problems. All you need to do is memorize the solutions to each of those 5 questions, and when they show up in the test, you write down the answers, right? But clearly, that's not what we want in our neural networks, and in fact, that's not what we want in our students either. We want them to be able to answer questions that were not the ones that they memorized, right? So that is where this class comes in. So if you choose a class that's very big, it will just memorize, right? But if you choose a class that's very small, then it won't be able to predict a good answer. So you need to choose a class that's somewhat intermediate, and that's where some of the tricky part comes in, right? Does that make sense, Vishwa?
Yes, of course, yeah. I mean, so that's what the job of these analysts is, the people who get a job in machine learning?
Yeah, that is one of the big jobs. So there are several different kinds of jobs that people get in machine learning. There is of course, there's all the research that's going on in machine learning where people are trying to come up with clever ways, clever designs for neural networks, or like some people try to experiment with different nonlinear functions than the one that I mentioned, even though the one that I mentioned is the most popular one. It's called rectified linear unit, which is a really fancy name, but it's a very, very simple function. So yeah, so there is that class of people. And then there is another class of jobs that people do in machine learning, which is given a problem, find the best possible solution without actually trying to invent new architectures and new algorithms, right? So those are called modelers typically, or modeling engineers. And there are a lot of those all over the world.
Hey, Vineet, Rajiv again. So two questions. So one is alluding to what you mentioned some time ago about it not being clear what the layers represent. I thought one of the findings of deep learning research was that these intermediate layers were representing more advanced concepts.
That's right. Which is, given a problem, find the best possible solution without actually trying to invent new architectures and new algorithms.
Hey, can everybody else please go on mute?
Okay, yeah. So Rajiv, you are absolutely right, and that's our hope, that these intermediate layers do represent high-level features. So, for example, in our brain, this is what we sort of see, that the input, of course, is the light that's coming to our eyes. It's like pixels in an image. But internally, the brain will try to determine higher level features like, oh, there's a line here. In fact, some of that is done in the retina itself. But the rest of it is done in our visual cortex, which has about 6 or 7 layers. So, and each layer is trying to get higher and higher level features until you eventually say, oh yeah, that's a car, that's a person, that's a tree, and so on. Yeah, you're absolutely right. That's our hope. But when we are designing these neural networks, we often don't care about what the internal representations are, right? Although there is, of course, people in research try to do that most often, but typically modelers don't care about this.
Correct. And one more thing. So isn't there some nice properties of neural networks which ensures that there are that you may have a lot of parameters, but the number of data items needed to be able to learn weights is not that large. So basically, overfitting does not apply.
So that problem is something that I've not seen a satisfactory solution or a satisfactory explanation. This idea of why don't neural networks because neural networks will often have hundreds of millions of parameters, and so they should just be able to memorize the xi's and yi's, right? But typically they don't do that, and we don't have a good explanation. Maybe I'll come later to a point in the next slide. I'll talk about one possible reason why they don't memorize.
Exactly. So I actually heard Sanjeev Arora one of his talks, and he made this this point, and I was like, wow, okay, but go on.
Yeah. So typically one should have expected it. It doesn't happen in practice, and I'll talk about it in the next slide. Okay.
Yes, Abhishek this side. I just want to ask one question that the number of layers in the neural network, does it play any role in the accuracy part?
It is not clear. So we have done experiments within Google where sometimes instead of making the layers bigger, we make them smaller, but we have more layers. And typically, we have found that the answers tend to be the same level of quality. So, but yeah, it depends upon the amount of memory you have and the amount of computation you have. Yeah, so often people are trying to build deeper and deeper networks. By the way, the part about deep, when you say deep learning, it just means the number of layers is large, right? That's the depth of the network. So yeah, there are two ways of making a bigger network. One is you make it wider so that each layer has lots of units. And the second is you make it deeper, that there are many more layers. And both of those can be used to make the network more accurate. By the way, I should caution that accuracy is not something that is guaranteed by making a network larger. Sometimes if you make a network larger, it will just memorize all your input training examples, but will do poorly when you give it new examples, right? So one has to be careful about just making the network bigger and making it more accurate. It's not always going to happen.
Sure.
So sometimes a smaller network may be more accurate than a bigger network.
Sure, and one more thing on what you just mentioned about it being a topic of research about figuring out what class of functions will work better. I thought Google also released this paper on neural or product called NAS, Neural Architecture Search.
Yes.
Is it trying to address that same problem?
That's right. So they're trying to address the problem of, let us try to sort of automatically try and find the number of layers, the size of each layer, and so on, by just doing a brute force or some kind of search, right? So, and see whether the answer becomes more or less accurate if you increase the number of units, increase the number of layers, and so on, right?
Sure.
So, so now here I had mentioned that the the function is going to try and make a prediction, and we want these predictions to be close to the expected answers. And this is made more precise by choosing what we call a loss function. So the loss function is a function that just measures the discrepancy between the expected output yi and the computed output yi hat, right? And this can be something very simple. It can be just the distance between these two in the standard geometry, right? Yi is a vector, yi hat is a vector. The distance between them is my loss function. So this is a very commonly used loss function. And there are many, many others, right? So this just measures how bad my answer was compared to my expected answer. And now if I add all the losses on all the examples, I get a function just of the parameters w. Yeah. And this function is the function that I'm going to try and minimize. And now now the problem is completely specific. Right? We have a function of w, the function of w, which is the parameters, and we want to find the best function, which is the one that produces the least discrepancy between the expected and predicted. And so now we want to find just the minimum of this function, right? This is a problem in calculus. I hope this is all familiar to you now. We are trying to find the minimum of this function w.
So Vineet, this is still in the training set, right?
Yes, we are on the training set, and actually the optimization problem is only going to deal with the training set. It does not worry about what happens outside the training set. That is the problem which is dealt with by choosing the appropriate class, by choosing the architecture of the neural network, and so on. Right? The optimizer merely cares about finding the best function on the training set.
Perfect.
Does that make sense?
Yes. Thanks.
Essentially, we are trying to reduce the problem and the abstract problem of finding the best function to solve a particular problem to a mathematical problem of an actual function that we can try to find its minimum. Right? So this is now we are in the M101 territory. And so now the problems that happen, so now of course, we all know how to minimize functions. You take the derivative of the function and set the derivative equal to 0, right? But the couple of problems that happen here is, one is that this function is a function of very many parameters. This W, as I mentioned, can have hundreds of millions of entries. So if you just try to minimize it directly, you probably won't get the answer in a finite amount of time. The second is that the form of this function is also pretty complicated. So each individual entry here is given by the network, which is pretty complicated itself. But then you're adding up over all the training examples, which can be in millions or billions or trillions, right? They're a very, very large. So the function is fairly complicated. So we can't minimize it directly. So then there is the other method of finding the minimum that some of you may remember, that you start at a particular point randomly. Then you find the direction in which the function is decreasing, and you move a little bit in that direction. Then you again find the direction, and you keep moving there until you find that the function is not decreasing in any direction anymore, and that therefore must be a local minimum. Right? This is just, again, straightforward calculus stuff. But the problem, once again, is that even at a particular point, to find the direction in which the function is minimum involves evaluating this very large function and its derivatives, which is also very difficult. So about maybe 20 or 30 years ago, people came up with a framework. No, actually even more earlier than that, maybe about 70 years ago, people came up with a framework of minimizing these very large and complicated functions. And this is the framework called stochastic optimization. Right? So here is the idea. So you start off with a network that has already been given to you. And your goal is to find the W that minimizes this function, the loss function, right? Is this clear so far? Any questions? So now here is the algorithm that we will use to find this minimum. So first of all, we will start off with some random value for W. And this is really done using random number generators, right? So we will give that as our starting point. And now at each point, we have this starting point. And I will show you how to get to the next point. So now you take some examples from your input example set, right? Instead of taking all the examples, you take some, let's say 100 of them, right? You make your prediction using the network that you already have. So the WT is saying that use the current set of parameters. You make your prediction. You find the correct answers. You find the discrepancy between the correct answers, and now you can find the derivatives. And these derivatives are now possible to compute because the function is only going from 1 to k, where k is maybe 100 or so, right? So you find these derivatives, and now you use these derivatives to move in the direction that minimizes the function a little bit, right? And that gives you your next point, and now you keep going back and forth. So this is the, sorry. Yeah.
So Vineet, in every round, do you use the same set of 100
no.
sets or different ones, right?
You use different ones. And in fact, this is the interesting thing, that those 100 guys are basically sort of a sample of the total set. And essentially what you're saying is that the gradient that I want, or the loss function that I want, is computed by a sample. So it's like, we do in life, right? You want to estimate how many people are going to vote for one person versus another. You ask the 100 people.
Exit poll.
Yeah. And then you come up with an answer, right? And then you ask a different 100 people every time. So you will get, you will slowly converge to the answer. Right?
So Vineet, a quick follow-up on this. Basically, it boils down to whoever is able to provide a loss function which is really able to minimize the discrepancy. That is basically a most accurate and predictable learning part within machine learning, right?
Actually, even that is not so particularly important. There are a few loss functions that many people use, and the distance function is one of them. But typically the loss function plays some role, but it's not a very, very big role in machine learning. The biggest role really is in the data set and in the architectures. The biggest role is of the data set. If you have a lot of good data, you will be able to come up with a good answer.
No, correct. But for a given data, where I'm coming to is taking an application of this. Whatever I'm trying to apply machine learning to, assuming I have a given data set and there are 5 service providers who claim to offer a machine learning solution for that data set. So given the data set, obviously among the 5 service providers, whoever will be able to minimize that loss function to the absolute minimum would be a fair indicator of whose solution is more accurate, given the data set.
That is to some extent correct.
Correct.
It is correct in that is what the optimizer is doing. But of course, when you get the solution from the provider, you will want to apply it to some data that they haven't seen.
Which is fine. That is a calibration part and the actual learning beyond the known data set.
Yes.
Correct. Now, Dambu, my question is, when there are several machine learning solution providers, are there these loss functions that they're reusing, or everybody's reinventing their own? What is the industry norm? So are there fungible codes for the given data set, or are people developing their own codes? What exactly is the commodity out there in the machine learning market?
So it depends upon the provider. If you're a sophisticated provider, you will probably invent your own loss functions. And we at Google, we use some pretty complicated loss functions. Actually, I shouldn't say complicated. I should just say that those loss functions are the sum of different kinds of losses, right? But mostly the loss functions themselves are just pretty straightforward functions. There are like about half a dozen of them that are available in the literature, and you mostly end up using those. Now, you can, of course, have different objectives. Like, for example, your objective when you're trying to help somebody, say you're trying to make somebody buy an item, right? You're trying to predict whether a user will buy the item or not from a page. So your loss function could be a very simple loss function, which is, did they buy the item or not? But your goal is also not just to make them buy the item right now, but to have a long-term customer, right? So then you might also want to input into the loss function whether they were happy with the item or not after they bought it, right? So maybe you send them a survey, and the results of the survey is also made a part of your loss function, right? Suppose they were very unhappy after they bought the item. Then you might want to say that, hey, Mr. Network, do not predict that this user should buy this item, right? Or don't show this item to this user because this user was unhappy with this item. Do you see what I mean?
Absolutely. So the richness will obviously determine upon how many dimensions you are able to add, not just a single dimension of buy and sell. So you can always make it richer. Yeah,
you don't want your customers to be unhappy. Like if you show them items that are very flashy and maybe they will buy it, but then they will feel unhappy afterwards that they bought these items. You don't want that kind of thing to happen. So you can incorporate that into your loss function also.
Got it. Thanks.
Right. So at this point, we've got our next set of weights, and we go back to the beginning, and we keep going round and round. And this is ideally we should stop when the gradients vanish, but in practice we don't do that. And this is actually, I think Rajiv had asked this question about how do neural networks not memorize. Typically they don't memorize because we stop them from training all the way to the minimum. And I don't know a lot of the theory behind this. There is some theory, not too much, where it says that, well, stopping early is probably a good thing on new examples, right? If you let the neural network train all the way till it finds the minimum, then it is going to work very well on the input data, but it is not going to work very well on the rest of the examples that were not given to it, right? So this is basically what the algorithms keep, the neural network training is. These days, this is the standard method, right? Now, I put one line in red, and that is because that is the secret sauce that different optimization algorithms have. How do you use the gradient to move from one point to the next, one WT to the next? And that's where all the work in machine learning optimization is. Everything else is pretty standard. So let me talk a little bit about a couple of algorithms, and then we can decide how long we want to go. So the first algorithm, oh, by the way, yeah, this is something that I wanted to mention. How do you know that your algorithm is good? So here is a measure of an algorithm that I learned. It's called the regret. So it has a very interesting name. And the idea is the following. Suppose somebody came and told you that, hey, here is the best possible value of parameters for your problem, right? This is the absolute optimum. Then what you can say is, well, I had these batches of examples come in one at a time, each of which was predicting a particular loss according to me, according to my current set of parameters. What would the best algorithm have done in that case? That would also probably not be completely correct because, given in the Avinash example, given a page and a buyer, some buyers will buy it, some buyers won't buy it, or the same buyer may buy it at one time and may not at another time. So your example, so there is no perfect optimum W, right? There's no perfect W, but there is an optimum W, which is, let's say, the best possible so far. So now you can compute the difference between the two. What is the total amount of loss that the best possible W would have incurred versus the loss that my algorithm incurred during training? And we call this the average loss, the regret, right? And if you can prove that your algorithm will have, the regret will converge to zero as time goes to infinity, then you say that you're very happy, this is a good algorithm, right? So this is sort of where some of the theory of machine learning comes in. You're trying to prove this regret bound.
But then is this optimum W not a notional?
It is not. No, there is. I mean, you have the set of W's. It's a space, right? And every function has some minimum on every space, right? These are, these are not functions that decrease to infinity because the L is actually a positive function. It never becomes negative, right? So for example, you know that if all the L's become zero for some particular W, then that is the best possible W.
But then that was a function of how long you tested, because you said you run out of time and patience.
Correct.
So it is within the sample space.
So this is a theoretical construct.
Correct.
Right. So this is when you want to prove that your algorithm makes sense. If your algorithm doesn't even satisfy this, then it's probably not so good. And that's where the mathematics comes in, right? So there is all the engineering that I talked about, which is how to design the network and so on. This is where the math is. And optimization is, of course, an interplay between the mathematics and the engineering.
Got it.
Right. Now, this is a very strong requirement that regret goes to zero, because this will go to zero only if your algorithm is always able to find the best possible W, which in these extremely complicated functions, it probably won't be able to find, right? These functions are not, they're not like nice bowl-shaped functions. They're very, very complicated looking functions. So there are many local minima, millions of them, in fact. And your algorithm will probably find a local minimum, but probably not be able to find the global minimum. So having a convergence proof is good. If you don't have a convergence proof, you probably have not a good algorithm. But even if you have a convergence proof, it doesn't necessarily mean that your algorithm is going to work well. And this is sort of the game now, that we are trying to find algorithms which we theoretically show converge, but we also have to show that they work well in practice.
So Vineet, what was T again here?
Time, just the number of steps.
Okay.
Right, the number of rounds of that algorithm.
Okay, perfect.
Right. So I won't talk more about this at all. In fact, now let's go to some common optimization algorithms. So the first algorithm actually came out in 1951. Right. So you can see that this whole field, while there is a huge amount of hype in the last 5 years, the field is actually very old. It's like about 80 years old. Right. So this first algorithm was in 1951, and the idea is very, very simple. So here, we are at a particular point, Wt, right? We are trying to find the minimum of this function Fw, right? Now I don't need to worry about examples and all, we're just talking abstractly. So what this algorithm does is, it finds the gradient at Wt, and then it is going to try and move in the direction opposite to the gradient. That is where the function is decreasing the fastest, right? But when you're doing that, you also don't want to move all the way, because remember, our gradient is only an approximation to the real gradient, right? Because we just took a sample of the input examples. And also the gradient is changing at each point. So we move a little bit in the direction of the negative gradient, but not all the way. And this can be expressed as follows. So you will take, you have two things that you want to do. One is you want to move in the negative direction of the gradient, which is or you want to minimize the loss. The second thing that you want to do also is you want to stay close to the current point, because you know that it was probably pretty good, right? And you can interpolate between these two by just taking a sum of these two. And then there is a constant here, which says how much importance do you want to give to staying close to the current point versus decreasing the loss, right? So in the beginning, of course, you want to decrease the loss because your current point is probably no good, right? You had started from a random point. So you take a large value for the this constant eta, right? So that this first term is not very important, the second term is important. But after you've seen a lot of examples, you think that you're probably at a pretty good point. And now if your gradient is saying, hey, go that way, you don't want to go all the way, because all this learning that you've had from previous examples that you don't want to forget, that is sort of encapsulated in your current location. So you will decrease the eta and give more importance to the first value, first term in this function. Is this does this make sense? Any questions here? So I hope I'm not losing all of you right now.
No, this is perfect.
Okay, so now we have a function, and now we can use basic calculus. And I would invite all of you to try and do this. This is what we get. That Wt plus 1, from this, just by taking the derivative of this with respect to W, you can see that it is W minus Wt times 1 over eta is equal to the gradient, which is Gt, the gradient of this loss function. And if you solve that equation, you get this standard update, right? This is called the stochastic gradient descent update, right? So in every step, you will start from your current step, go in the negative direction of the gradient, but only a small amount determined by that eta. And if you decrease, and in order to make the algorithm sort of converge, you want to decrease that eta slowly as more and more steps happen, because you don't trust the gradient as much later on. You trust your current point more, right? So that's sort of the intuition behind this. And in 2003, Mr. Zinkiewicz, who came up with this idea of regret, also proved that this algorithm will converge. Its regret is of the order of 1 over root t. So as t tends to infinity, the regret will tend to 0. So this is one of the most common algorithms even today. This is one of the most commonly used algorithms, which is very interesting since it was invented almost 70 years ago, actually, right? But this algorithm has some problems in some cases. And here is an example. So if your loss function, and let's suppose that the loss function we represent as, there are only 2 parameters, and if your loss function looks like the left-hand side, right? And these are contour lines. So essentially, I'm trying to represent a sort of bowl-like thing, which is very elongated in one direction than the other, right? So this is the representation of the loss function as contour lines. So now if you imagine the stochastic gradient descent algorithm that I just mentioned, it will always move perpendicular to the current line, right? That's because the gradient is always perpendicular to the contour line. And this is, by the way, true, right? So you want to get from here to here. And so in the left-hand side, so what this means is in the left-hand side, you were just computing the distance using the standard metric, using standard Euclidean geometry. But on the right-hand side, we will use some matrix in the middle. And this is the matrix that is used to rotate the axes and scale them. And this metric, by the way, is named after P.C. Mahalanobis, who was a statistician in the Indian Statistical Institute in Calcutta. So this is the Mahalanobis metric. And the matrix H, which determines this metric, is the matrix that is rotating the axes and making everything more spherical. So for those of you who are familiar with the Hessian, something that you might have learned in calculus classes or later on, the second derivative of the gradient, the matrix consisting of the second derivatives. What we are trying to do is we are trying to convert the space into one where the Hessian has it sort of looks nice, closer to the identity matrix. But again, don't worry about this if you don't remember this. The idea is just that we want to change the geometry. And the reason why we want to change the geometry is because our algorithm is otherwise oscillating a lot. Of course, you don't have to change the geometry. You can try doing better with just the stochastic gradient descent by making sure that it doesn't oscillate as much. When should I stop? Vishwa?
Hey, there's no limit. It's up to you.
No, I mean, people want to go to sleep also, right?
No. It's fine.
35 of us are still on, so keep going, Vineet.
Yeah.
Okay. All right. So this is the first method that people started using, and it comes from the idea of physics. In physics, where if you're oscillating a lot back and forth, if you sort of make your object heavier, then if you're applying forces in different directions, it won't move too much, right? So the problem is that our gradients are noisy because we're taking a small sample every time. And instead of taking this actual gradient, let's take our average of the past gradients also, so that we don't move, so that we don't sort of get a lot of whiplash. And this method actually works extremely well. And in fact, whenever you see stochastic gradient descent being used, it's almost always used with momentum, right? So you're averaging out the gradients a little bit so that if you're going back and forth, you can see in that particular example, this will work fine, right? And now your momentum step is going to be just the same as the step that we had before, except that you will, instead of moving in the direction of minimum descent, you will move in the direction of, in the direction of maximum descent. you will move in the direction that is sort of an average of the previous maximum descents also. And this is just acknowledging the fact that our gradients are noisy, right? So we are trying to eliminate the noise a little bit. So this works extremely well, but there are other methods also. And people have, of course, come up with lots of alternatives to these, which I won't go into, right? The next method is if we can do a second order approximation. And this is again using Newton's method. So the idea is the following. Instead of approximating and just moving in the negative direction of the gradient, let's try to find the second derivative at that point as well, right? And then you can, instead of moving in the negative direction of the gradient, you can try to construct a little parabola around the point, right? And find the minimum of the parabola, and that's where you end up, right? So instead of, so that tells you sort of how far to move and where to move to. So this is a very powerful method. It works extremely well. And the way it works is as follows. You want to minimize FW. You first write down the Taylor expansion of FW. And remember, this is all stuff we studied in M101. So the function FW around the point WT, this is the Taylor series. We are going to take the second derivative term also. So the first term is, of course, the function here. Then there is then the second term gives you the direction of the gradient, and the third term gives you the direction based on the second derivative, right? So now that you have this Taylor series approximation of this function, you can minimize it again using calculus, and you will get this as your answer. And again, people who want to should actually go ahead and try and work this out. This is not very difficult at all, right? So notice that now we have a little matrix here, which we are going to multiply the gradient by, and that sort of corresponds to the rotation, right? This del square f of WT is a matrix. We're taking its inverse. So we are sort of making the whole space more spherical.
So Vineet, one question. I mean, you had mentioned that the gradients can be noisy, for example.
Right.
But if you're doing the second order approximation, won't that be even noisier?
Yes, and that is definitely a problem in this approach.
Okay.
Yeah, and that is why this approach is not used in practice, I must say. And the biggest reason that you can see is that the second derivative matrix is going to be very, very large, right? If your function has, say, 100 million dimensions, then the second derivative matrix is 100 million times 100 million, which is just impossible, right? So this method is not used in practice, even though it's a super fast method. It works great, by the way, when you have a small dimensional problem, in which case, of course, you know, the noise is gone. You find the exact gradient every time. But in machine learning, this method is not used. And by the way, this is just another alternate view of this method. It is formed by taking the loss function as we had before, and you want to stay close to the current point, but the metric that you will use to measure is given by the second derivative matrix, right? So now the problem is that computing this matrix is very expensive, and we don't use this in practice. People have come up with all sorts of approximations to this, and that turns out to still be very expensive, right? So the third method that I want to talk about, and I think I will stop after that, is the method that was invented at Google in 2010. So both of these teams were working at Google at the same time, and they came up with this method approximately at the same time. So here the idea is that instead of finding the second derivative matrix, we find the correlation matrix. So given a gradient, we find its covariance with itself. And this gives us a matrix that we will use to now compute the metric.
Yeah, 2 tens here.
Right?
Do you have more cash?
That's it. I barely use cash.
Hey, can everybody else please mute?
So I won't go into why this is how to derive this matrix and all. But the idea should be pretty clear, right? This is just the covariance matrix, the second moment matrix, and from this, these folks were able to derive a very nice algorithm, which I'll just let it be here. So instead of using the second derivative matrix for the Mahalanobis matrix, they used the second moment matrix, and they came up with an algorithm called Adagrad, which again uses the update is very simple. It just uses the second moment matrix to change the gradient and make it more spherical. And they proved all sorts of nice properties. Again, the problem is that this algorithm is very expensive. The matrix is still the same size, and it is also, again, difficult to compute with. So then they came up with an idea that is probably the second most widely used algorithm today, which is called Adagrad. And here they said, well, let's just keep the diagonal of that matrix. Now we are in good business, right? The diagonal is the same size as the original number of parameters. So if you had 100 million parameters, you have a matrix. Instead of keeping the 100 million by 100 million matrix, you just keep 100 million values. And there's a very nice intuition behind this, which is component-wise, this is what your update rule looks like. So the learning rate, the constant that I had used, that eta constant, is now specialized to each parameter, right? So originally we had one parameter for all the components of the vector, and now we have a separate parameter for each. So this algorithm works very well in practice. It's O(n) space, O(n) time, and it is used very widely. So now I think I should stop at this time.
So Vineet,
yeah.
I mean, as you mentioned, I mean, this neural networks field is very, very old. And I mean, even when I was a graduate student, I had many courses and people were working on it and so on.
Yeah.
So, I mean, is this the latest thing that you showed, the optimization, the Adagrad? Is that what changed the game, or is it just that we have more and more compute power now available? Because I remember around 2010, I mean, there was this huge noise about this is going to change the field of machine learning, because even the founder had said some point said that, hey, this field is dead, kind of thing.
Yeah, so there were actually 2 or 3 things that happened. One was definitely compute power. People started using GPUs, and this huge amount of power sort of allowed us to train neural networks. What happened in the 70s and 80s when people tried to train these neural networks using these algorithms that I mentioned, stochastic gradient descent and the stochastic optimization, they won't just converge, right? And in fact, even today, if I use my CPU, I tried to use my CPU to train a network a couple of days ago, and after 24 hours, nothing had happened. But on GPUs, that same network will get trained in less than a few minutes. So compute power was the big difference. The second big difference is the availability of lots of data, right? In the 70s and 80s, if you had 10,000 training examples, it was considered a decent large training set. Now we have training sets that are in the trillions, right? So the availability of data has made a massive difference. But of course, you can only use that data if you have a lot of compute power, right? So these 2 things put together sort of changed the field. And of course, we are coming up with better algorithms. I mean, in the 70s, there was no backprop, the algorithm that is used to minimize. And that came in 1985 or so. And other optimization algorithms and other different algorithms have been coming in. So, but the field has basically become big mainly because of engineering and data availability.
And what about the architecture? So new architectures coming in.
Yeah, new architectures have also come in, but you can't train a new architecture is not useful if you can't train it.
Yeah.
And the only thing that allowed us to train these newer architectures was the availability of large amounts of data and large amounts of compute power.
Yeah.
So Vineet, this is Shalab. What do you see the application of these things in?
So, for example, Adagrad is the algorithm that was being used to train pretty much all the networks inside Google, right? We have neural networks that do prediction for advertising. So given a user and an advertiser, and we can actually predict what is the likelihood that this user is going to click on this ad, right? And if we can do that, then we can decide that, oh, we should show the ads on which the user is more likely to click than just show the highest bidder. Does that make sense?
Yeah.
Right? So because that way the user is happier, they're seeing ads that they are, more of greater interest to them. And meanwhile, the advertiser is also happy because their money is not being wasted, right? And Google, of course, is happier if the users find what they are looking for. So that is one application. Then another application is in search, where we are trying to find, is this page of interest to a user who asked this query, right? So again, we make a prediction, and then we have lots of training data because in the past, our users have clicked on different pages, and over like many billions and trillions of examples, we can figure out that this page is definitely of greater interest to this user. Other examples are, for example, machine translation. So these days, if you go to translate.google.com, then you can actually see that you can enter a text in any language and out will come a text in a different language. Now, this field has been around for a long time, but neural networks have pretty much completely displaced all other methods, right? Because they are just far more accurate.
So, Vineet, I have to say I learned way more than what I learned in entire math at IIT. I learned more here because maybe I wanted to learn.
Well, I think it is useful to have some kind of goal or application in mind. When we were taught in IIT, I mean, I learned linear algebra in a class in like M203, I think. Oh no, not M203, but I think one of the optional classes. And I must say that I found it very boring.
We had a good discussion around this.
Yeah, I did extremely well in that class, but I still found it extremely boring, and I didn't understand the use of linear algebra until after I took a class in the EE department in my final year, in my final semester actually. So in my final semester, I took a class on coding theory and cryptography.
Oh,
and suddenly taught by Professor M.U. Siddiqui. I don't even know where he is now. So suddenly I realized that this is actually interesting stuff. You can do stuff with linear algebra. Like otherwise, we were taught, hey, find this eigenvalue. Okay, we found the eigenvalue. We have the formula. What's it good for? I don't know. The teachers never told us what it is good for.
Yeah, I mean, I started liking it a little bit after I got this book, Introduction to Applied Mathematics by Gilbert Strang, where he explains it through nature, how
so Strang has a book on linear algebra and learning from data. So he actually has a book that combines machine learning with linear algebra. And as you can see, linear algebra is everywhere. We were using matrices and vectors and so on at every place in this discussion.
So Vineet, I mean, I have one request to you that, hey, I mean, can you look at applying some of this to the field of medicine?
Oh,
there's such big problems happening. I mean, instead of advertising and others, I mean, I feel like people like you can change the field of medicine.
So this is already being done, right? So both we have a large team, and of course we have Navdeep Sood, who is using machine learning to medicine all the time. So yeah, this stuff is happening today everywhere. Medicine is one of the prime areas in which machine learning is playing a larger role. So for example, people are using machine learning to recognize tumors from X-rays, right? You feed them an X-ray just as a bunch of pixels, and it will point out not only where the tumor, if there is a tumor, but it may even tell you the part of the image where it thinks the tumor is. And then you can immediately give it to a radiologist who will say, yeah, that's correct. Now, of course, I must caution that I don't believe, at least at this point, neural networks are at the point where they can just replace the radiologist, but they can definitely help the radiologist.
Yeah, IBM has put their Watson Health for sale.
Yeah.
Okay.
Yeah. So
this came out recently that they were not able to commercialize it as effectively as they had wanted.
Yeah, but so that is why I think it's useful to have applications that are going to change the world, and it's also useful to have applications that make a lot of money. Right?
Yeah.
No. I mean, I was more leaning towards, not just, identifying what the problem is, but actually more towards finding cure.
Mm-hmm.
Yeah.
Actually, Vishwa, there was a nice article in Wired magazine about a couple of months back about COVID and how the vaccine maker actually resisted using artificial intelligence because of mistrust on it. So I think it is more of a psychological also whether doctors really want to use it or not.
Yeah.
So,
and that will slowly change. Because
it will take time.
One of the things that will change this is the question that was asked about explainability. How do you explain whether a neural network, what did it do? And a lot of work is being done in this area. It's a very active area of research where you want the machine learning system to come up with a human understandable explanation. Right? Where the doctor says, the machine learning system says, I think this person has this disease. So the doctor says, why do you think so? And then the system comes up with an explanation saying, oh, because, this person has high fever and he's also coughing, and therefore ... right? And then the doctor can say, yeah, that makes sense. Okay. And the reason why the network can do better than the doctor is because the machine learning system can first of all be up to date with the latest research, which is difficult for doctors given the volume of research. And secondly, they can also be able to summon all of that research at the same time, right? So there may be diseases that the doctor is not very familiar with, but the machine learning system, having looked at all of this, can all of these papers can say, oh yeah, there's this new piece of data that came in.
So Vineet, is there, by just way of a rule of thumb, any minimum size of the data to make any business proposition viable for machine learning? Should it be like at least 1 million data points, 10 million data points, 5,000 data points?
I don't know of a rule of thumb like that. It depends. I mean, so in medical field, for example, even few thousand data points are difficult to get, but people have been able to find results even with a few thousand data points. I would say anything less than a few thousand data points is probably not going to work, but there's no upper limit, of course.
So
Vineet,
Hi, Vineet, Alpan here.
Hi.
Really enjoyed your talk. I wanted to know your views on a couple of things. One is the optimization methods you mentioned are all local optimization methods, right? So they find a local minimum.
Yes.
And I haven't seen much work of late on global optimization methods like, genetic algorithms or Markov chain Monte Carlo and so on, which used to be popular earlier on, but nowadays I don't see much. So do you have a view on that? That is one question.
So one problem with global optimization is that these loss functions are extremely complicated.
Yeah.
So with hundreds of millions of dimensions and hundreds of billions of local minima, finding the global minimum is very difficult. But the other interesting thing, and this is something that has been empirically observed, there's no justification in practice, is that it seems like most local minima work pretty well. It's not like
that's the funny part. It's not clear why that is the case. Right?
Not at all. Yeah. So we don't know why that is the answer, why that is the case. But for example, if you like, remember in my slide on stochastic optimization, I mentioned you start off with some random point and then you do this procedure, right? And so there was a lot of randomness in the whole procedure. There was a random starting point, the random batch that you choose at every point, right? So, but it turns out that, so then if you run the algorithm again, it is very unlikely to give you the same answer. It'll probably give you some different answer. But it turns out that for the same algorithm and the same data set, starting from different points and choosing different batches often doesn't make a huge difference to the answer. Right. The quality of the answer will remain the same. So this is something that we don't have a good explanation for. Again, this field is, while it is 70, 80 years old, it's also still pretty new. I mean, it's much newer than say, mechanical engineering, which has been around for hundreds of years.
So along the same lines, Vineet, when I was a grad student, I took a couple of courses on multi-grid methods. Are you aware of those?
No,
because I mean,
yeah.
Okay, yeah. I just did a quick search, and there is a good amount of funding going into multi-grid methods for machine learning. Very recent ones. I think you should take a look.
So can you just say in a couple of sentences what a multi-grid method is?
Oh, I mean, it works hierarchically on the data set, not just at the bottom level. Yeah, so it propagates along different levels to find the global minimum.
Okay, I think that makes sense. But again, these surfaces are very complicated. So if your grid is not fine enough, then all grid squares will look very similar to each other.
Yeah. So I'm not doing any research in this area at all. I just wanted to make sure people are aware of that method.
Yeah. So Vineet, I would like to share a conversation I had with one of my colleagues some time back. Want to know your thoughts on it. So I was discussing one of the auditors at Deloitte, and I said machine learning obviously has a lot of potential in auditing, because whatever work you do manually and you take 6 months to come up with the gaps, a machine learning solution or algorithm could probably do it in minutes, given obviously the data available. And the only difference of opinion we had was I said that will typically throw you auditors out of the business. It will change that paradigm. And they said, no, in which case we will audit what the machine does. So I'm not sure, as you just now mentioned, that even if you work the same algorithm, the same data set, it will have a different route and a different starting point, and there's so much of randomization. Is there traceability and auditability of what the machine did, or you just get the outcome?
So currently, I think you get the outcome. By the way, I don't understand what auditability means, right? So, I mean, of course, if you fix the randomness, and we can do that. In fact, we can say that, okay, we're going to have the starting point be the same every time we run the algorithm. Then, of course, it will produce the same answers, right? So you can remove the randomness if you want to.
But then that removing the randomness itself will limit the utility of machine learning. Then it's no longer machine learning, right? Then it's just automation.
No, yeah, in a sense that is somewhat true. But on the other hand, if you remove the randomness, then the only thing that will happen is the machine will still converge to an answer. But the only difference is that if you try to train the machine again, it would give you the exact same answer.
Exactly. So that defeats the purpose. The whole idea is to go beyond the human realm of what only we can do, whereas the machine can do all those perturbations which were humanly impossible in the same time with
No. I think you are. My point is slightly different. Your goal is to come up with a function,
correct,
right, which will produce for you a good answer. Now, if you fix the randomness, it will still come up with a function which will be pretty good, and it will work in practice on new data and so on. The only difference is that if you try to search for the same function again in the same class with the same input data, it would come up with the same answer. Yes. And that's not a bad thing necessarily. So it's not just, so it is still machine learning in the sense that we are still coming up with a function that will produce an answer. It will produce just the same answer every time. And that is exactly what you would like for auditability.
That is what would preserve auditors in their business, not necessarily that is the required outcome.
So the randomness is not a critical part of the machine learning. That's all about what I want to say, right?
Vineet,
it is there, but it's not super important.
I have an education question. In my company, the neural networks, we work in supply chain, and we try and make predictions based on history, and regular statistical techniques have been long used, and machine learning is exciting. Neural networks have not found much traction because of the explainability topic that we have been discussing, and humans don't want to trust the answer. So they've been, we've been using other techniques such as boosting and something cyclic boosting that we have come up with and whatnot. From your talk, I understand that ultimately it is about the trick is in minimizing the loss function, but the work that you have been doing, is it all focused on neural networks as the primary method for machine learning? What about some of the other methods such as boosting? And do you have a view one way or the other on that?
So
are those techniques more applicable for certain classes of problems?
That is, so boosting definitely is very helpful for explainability because the rules are pretty straightforward and are easy for a user to look at. So we are definitely looking at boosting. In fact, I have an intern right now who is looking at combining neural networks with boosting.
So Vineet, what is boosting for people who don't know?
So boosting is it's an older technique that was, the idea is, in fact, the specific idea itself is probably less important. The idea is to come up with a very simple set of rules. And so your rules will be like, if there is more like blue in the picture, it's probably a sky. And if there is more red in the picture, then maybe you're close to a volcano. And so there will be many, many, many such rules that are going to give you a prediction, right? If you see like two oval-shaped objects right next to each other, they're probably eyes. If you see some eyes, then there's probably a face in the picture, right?
Yes.
So you are trying to learn a lot of these rules, and there are various techniques to do that, and boosting is one of them. But the main idea is that you want to learn a lot of simple rules that can give you a good prediction. Now, boosting by itself has been superseded by neural networks in the last few years. In terms of its accuracy, it's not as accurate. But in applications where explainability is more important, and that happens to be a large number of applications, boosting is still found to be very useful. So one of the things that people are now trying is combining the two. So the way you combine them is you first learn a neural network to explain your data, and then use that neural network to teach boosting, right? So eventually you will get a boosting model, or it's like a tree model. Let's call it a decision tree model, right? So eventually you will try to learn a decision tree model from the neural networks. And that turns out to be helpful.
Yes. So this is Navdeep. This is like हाथी के दांत खाने के कुछ और दिखाने के कुछ और. In the sense, loosely, we are building two models. One to make a prediction, the other to explain what could be happening.
No, actually, you can use the boosting model eventually to do the prediction also. But it turns out to be helpful. So one of the things is that when you have a training set, some examples are going to be harder than the others. So if the boosting, if your method is going to focus on the hard examples, it might find it very difficult. So what a neural net might be able to do is figure out which of the examples are too difficult and say, inko jaane do, forget these. Let's try to focus on the other examples and get them right, so that we get a higher prediction quality.
So that's right. So
yeah, okay.
I just want to say that this is like teacher in the sense the neural network creates.
It's a teacher.
It's a teacher for the boosting model.
Yeah. So in fact, this is called the teacher-student model of learning.
Yeah. So Vineet, I the way I understood it, I guess, is neural network is like a gut. We make a decision with the gut sometimes. And then after the decision is made, we try to explain why we made that decision, and that's the boost model. Is that a good analogy? Or
so the neural network itself is not really making the cut. The decision tree is making a cut.
No, not cut. By making a decision with the gut, you get this feeling that yes, this is the right answer.
Yeah. So in a sense, what you're saying is right. That yeah, you get, and in fact, maybe that's the neural network in our heads which is making the decision, and then you want to teach. You want to sort of crystallize it in a set of rules that somebody else can follow. Yeah, what you're saying is that makes complete sense.
But Vineet, I would have also thought, I mean, initially when this question was brought up by Puneet, it would be the other way where I mean, the feature set is derived by the rules on the initial data, and then the neural network takes over. But then that doesn't lead to explainability, I guess.
Yeah, these days, I mean, we don't do feature engineering as much anymore. So you just throw everything at the neural network, and maybe that's a disadvantage. So what we are currently doing is we just take whatever information you have, like the pixels of an image. So for example, 20 years ago, if you wanted to do image explanation or image classification, you would take your image, you would detect all the edges using the computer vision techniques.
Yeah.
And then you would assemble those edges into a larger object, and then you would build a simple classifier on top of that. These days, people have gone away from that and said that, oh, just give the pixels to the neural net and it will figure out what to.
So you do not even segment the image. Like, I mean, if there's an image of cat I want to recognize with cat sitting on the bed versus sitting on a table, or they will just throw everything in the kitchen sink and
That's right. So that is right. That's what is being done today. So the days of feature engineering, when we spend huge amounts of time, are sort of in the past right now. And in fact, computer vision, the field has changed so dramatically in the last 10 years. I was talking to a colleague of mine. He said that all the old in computer vision conferences, it's actually quite strange because all the old guys still insist that the techniques that they had developed for edge recognition and object recognition and all are very relevant. And the new guys, on the other hand, are using machine learning to just blow them out of the water.
Oh my gosh. Okay.
So it leads to a very interesting dynamic where
have you seen any applications in scene understanding?
Yeah, absolutely. Yeah. So in fact, there's this friend of mine has started a company that does something very interesting. So they are trying to help assembly lines in manufacturing plants. So what they do is they will so they have cameras mounted on top of a worker. So the worker is the worker is performing a set of actions, taking a screw, putting it in a particular place, tightening it, and then doing this for 3 different screws and then putting it on the conveyor belt for the next worker, right? So what these guys do is they just take a video of the worker as the worker is working. They segment this to determine the different actions all automatically, right? So the video will be passed through a neural net to eventually say that these are the actions that this worker is doing. Now they can have this sort of feedback system where if the worker forgets to tighten a particular screw, in real time, the video will be analyzed and the worker will be told, hey, you didn't tighten that enough, right? Normally you gave it 3 twists and you only gave it 1 this time. So this is an example of an application of machine learning where the worker suddenly can become a lot more productive because now the quality can be made a lot better. So definitely, so this is an example of analyzing a video and understanding it. Right.
So this comes under like unsupervised learning, then, is it?
No. So they will have supervised learning data initially. So they will have these videos and they will have some expert come in or the worker themselves say that, okay, this is what I do, right? And then from the training data, the neural net is able to recognize that these are the tasks that this worker did in this video.
So where actually is unsupervised learning in all this? Because I've seen news items where actually these unsupervised learning algorithms are learning the video games. I mean, I'm more interested in that part. So they're learning the rules of the game and even beating the best players at the game.
So that is a different kind of machine learning that's called reinforcement learning.
Okay.
Right. So reinforcement learning is when, so even in a game, I mean, there is a reward at the end, right? There is a rule that tells you whether you won or lost the game.
Yes.
Right. So it's not completely unsupervised. There is unsupervised learning is when you have lots of data and you're trying to make sense of that data, right? Without actually there being a correct answer or not.
Okay.
So Vineet, I think one of the examples I've seen of unsupervised learning, I don't know technically that is unsupervised or not, is in fraud and analytics. So the machines actually look at the user behavior, the way you click your machine, when you open your browser, which buttons you go. And if it's an imposter, it will definitely not work the same way. And then the machine is able to alert that a fraud is likely to take place, more likely in this scenario, when the user opened the browser, but instead of going to the right menu, he first went to the left menu. So there are applications on that.
I'm not sure that that is unsupervised. I believe that initially to train the network, you will have to say that this kind of behavior is more fraudulent or is fraudulent and this kind of behavior is not.
No, but again, as you said, there's no right or wrong in it. Each user is different. It just picks up over a period of time that for this user, this is the pattern. And when the pattern changes, it's not wrong, but it is a deviation and therefore there's an alert.
Yeah, so that makes sense. Yeah, that is an example of, it's like clustering, right? So, so basically you want to recognize that these are sort of the normal actions, and then this is a field called anomaly detection.
Yes.
And we use it for fraud detection at Google as well.
Correct.
Where if the system is not following a certain behavior, then if this is the normal behavior that we have observed so far, and then something is out of the ordinary, then we will try to detect that.
Correct.
Yeah.
So Vineet, here is an engineering problem. So oftentimes what will happen is that companies will have data from several of their customers, right? And some of those customers will give them the permission to use their data for training, and some and some won't. So in that case, later on, if one of their customers alleges that, hey, I hadn't given you permission and you are using my data for training, so we are actually in that space where that is a relevant problem for us. And one of the strategies that we have thought we'd use is that we just store the data sets that have been used for training any model, and when a particular customer complains, then we just rerun that training algorithm with that same data. But given all the randomness, is that a replicable behavior, or should it be, or is there work in research about computing distance between two models for us to be able to make that claim that, okay, even if they aren't exactly the same, they're sufficiently similar?
Yeah. So there are various approaches, and I mean, this is a very practical problem that we can discuss all kinds of approaches to, and maybe we can discuss this later. But one thing that you can easily do is, for example, you can feed the networks, the initial network and the trained net. So like, for example, suppose you train a network with and without this person's data, right? So now you look at the differences between the predictions. So you have your original training data, you have your original trained network, you have the trained network with this person's data, and then another trained network without this person's data, right?
No.
So you will try to now convince the user that the one without your data is much closer to the original thing that we were doing than the one with your data, right? Would that be
Yeah, no. So I think that that I get what you're saying. So you're basically saying that compare the results output by the models to see to just measure how close these two models are. Okay.
Yeah.
And basically not go down the path of replicating weights and comparing those weights.
Yeah, so that is one approach that you can, instead of trying to remove the random. So one approach is, of course, you can remove the randomness from your system. And that's definitely possible. You can initialize all the random number generators, because after all, eventually these are computers, right? There's no inherent randomness in any of them.
Yeah,
so you can remove the randomness by setting all your initial seeds. And this is what we do in some of our training runs when we want to write a paper, for example. We want to be able to replicate the exact same answer. So that is one way that you can do it. But a second way is to actually just look at the outcomes, right? And so essentially just say that, look, my network produces very similar answers to the one that we trained without your data. And in fact, the one that we trained with your data produces very different answers. For some examples. So for example, if this person's data was used in training, then it typically would work extremely well on that person's data itself, right? Because that was part of the training set. So now you can say that, well, look, our network doesn't produce those good answers with your data, but this network does.
I see. Okay, makes sense.
Okay, so
but yeah, we can talk about this later on.
Yeah, we were nearing the end of 2 hours, and then it just flew by, and only the front benchers are left. And I know some of us are in the learning mode. Some of you guys are also experts. So what I would like to say is, I mean, as they say that in theory and practice are same, but in practice they are different. I would like to hear some of your practitioners like Navdeep and Harsh and Puneet and Rajiv. I mean, if you guys are actually using it somewhere, we can have a follow-up talk. I mean, not directly following it now, but maybe in a couple of months, where we can hear some practical examples of machine learning, how it has fared in your domains. And if the theory and practice actually line up. Vineet has educated us all nicely. I'm ready to learn more.
I just saw that Vigyan wanted to say something.
Oh, Vineet, has anything changed fundamentally? Because I mean, we were doing AI and search in 60s, 70s, 80s, and then suddenly.
So as I mentioned, the thing that has changed big time is the availability of lots of compute power and lots of data. The other thing that has, of course, then changed as a result of this is that neural nets have now shown themselves to be useful in a lot of problems that the older systems were not so useful. And one example is translation. So like if you looked at a translator from the 70s, it was basically made by rules, right? So you would have rules like, oh, this sentence is noun, verb. So you would do a parse of the sentence, then you would look up a dictionary, and you would come up with really bad examples, right? The translation was definitely not human readable. It would barely give you an idea of what the original text was saying. But nowadays, in fact, about 3 or 4 years ago, Google switched to neural networks for machine learning. So first of all, we can do hundreds of languages. So in fact, our current system is more than 100 languages are translated one to another, right? So effectively 50,000 pairs of languages. The second thing is that sometimes, especially for the languages that have enough training data, the results are impossible to distinguish from a human translated text, right? So that is what has changed. So when we were doing AI in the 80s and 90s, the results were not nearly at the level that we would have wanted them to be, and they were definitely not very intelligent, right? But at this point, I mean, like there is this site called booking.com. I don't know if you guys have heard about it. It's a very large travel booking site. So they, of course, have their pages in multiple languages. So in the lesser languages, in the more important languages, I'm sure they have human translators doing the translations. But in others, they just use Google Translate to translate the pages for them. So for example, if you want to see their page in, say, Vietnamese, it's merely a Google translation of their English page. And somehow they are confident enough that they're able to put that in front of their customers.
Yeah. So, I mean, you said the two primary things are data and hardware. The fact that you had.
And then, of course, there is a lot of research. Algorithms are being built, but I would say that the biggest changes are data and hardware.
And hardware, a lot of the hardware is coming from I mean, chips and semiconductors.
Yes.
Will quantum computing play a role?
We don't know yet. Maybe. Quantum computing is supposed to be good at search, and neural networks, as you saw in the training, it's like a search problem. You're finding the best W, right? So it is very possible that it will play a role.
So if we build quantum computers and hardware, then
yeah. So quantum computers are already being built.
larger. Yeah.
But they're not there yet, of course.
I think the largest one has like 53 qubits or something like that. Yeah. So Vigyan, that long hair looks good on you, man. Long time no see.
I was having difficulties recognizing Vigyan when I saw him. I've never seen him in that shape, so it was like.
Actually, me neither. Even though he lives like a few minutes walk away.
COVID times discovery.
Yeah. I know. Vineet, this was a great talk, man. Really inspired me to maybe try and open my math book one more time.
It's
see if I
actually learned.
Your earnings will go down if you open the math book. Your earnings will go down. So don't do
it. Sandy, you might be right, man. Maybe I should open the other book. But no, it was really very, very motivational, man.
Very well done.
Vishwa has been pushing me to, on many other fronts, but. Just being part of this, I've been missing a lot of these things, and I feel bad that I've missed a lot of these things. But this was really, really good.
It's not the same when you watch the recording.
Yeah, I should, Vishwa. I think that makes sense, man. Vineet, just a quick thing. I think you talked about the practical, Vishwa. You talked about the practical stuff in here. I think it'll be good to look at that kind of a thing with. Every aspect, including medical. I mean, I heard I was getting off and on the network, but I heard some talk about the radiology and the what we used to call computer-aided diagnosis being now done with neural networks, as you said. So, love to hear more of that practical discussion at some point, because we're trying to get into this from the AI perspective, what we call clinical decision support, in trying to leveraging AI. It has been different other approaches. For different things, and the easiest one that we're looking at is sepsis. So it'll be good to have that practical discussion.
I'm sure there are people in our team, in our batch, who can give a great talk on that topic.
Yeah, I've already talked to Raj Shekhar, who's also here. He's quiet for some reason, but
yeah. So okay, maybe I'll break the quietness then. So yes, we are.
Show yourself, Raj. Love to see you as well, man.
Okay. Can you see?
Everybody turn on your video. Let's stress it out.
I just did.
Nice hair, Raj.
What's that?
Nice hair.
Whatever is left.
Yeah. Good to see you, man.
So we are, so again, Vineet, great talk. So we are, more on the applied side. We are users of neural network, as opposed to, developing the theory. And I've been working in medical space, and one of AI sort of practical applications, that we have built is for, essentially binary classification of heart murmurs in children. So it's a very common condition in kids, and they come in two flavors, benign and serious that need follow up. So that's what we have been doing, and as you said, it's very difficult. Data is very difficult to combine in medical space.
Right.
So, all these models that we have trained, using like 1,000 or 2,000, recordings. But yeah, that's kind of an example of an application. Another new application that we are working on, and we are still in the data gathering phases. Can we, have an app, with AI, built in to tell between different type of, strep, bacterial versus viral. So just right now, we are in the data collection phase. Just as people come in, just collect, as much data as we can.
That's
so yeah,
awesome.
we could use a lot of help, in just building new models, and also how to get more performance out of less data.
Very good. So maybe you should give a talk, and then we can discuss.
Yes.
Sure.
I mean, it's going to be scheduled shortly. So Navdeep, since you're still around, what have you been up to? I've heard quite a bit that you're doing some work in this field.
So
he's on WhatsApp most of the time.
No,
yeah.
He's here.
So yeah, there is a bot that does my work. So I'm, for me. So my team thinks I'm working, but I'm actually on WhatsApp. Or it could be the other way around.
Navdeep, we cannot see you, man. Navdeep, would love to see you, man.
Okay. I'm very happy to hear that. But
yeah, maybe everybody turns on their camera. How about that?
Yeah. So I don't know if my video is working. I don't know.
No, we can see you.
We can see you.
Awesome. Yeah. Awesome. So, first of all, Vineet and others have covered the healthcare angle very well. But I just want to say that there is no one healthcare. Healthcare is a very big field, and the one that I'm working in is called care delivery. So, and in care delivery, things are exactly like what Vineet described. I'll quote him. He said, AI will not replace radiologists or doctors or specialists. AI will help them make a better or faster decision. And and also we do things like, so we try to add value to the care delivery ecosystem by removing losses, in the sense, like we see today, at least in the US, 25 to 30% of the total money spent on care delivery goes into administrative tasks. So things like making sure billing is accurate. So we try to save money there. See, that is where the low-hanging fruit is. And also one very interesting thing where AI is very useful is the example that Vineet gave about image processing being used to alert a worker that he or she did not tighten some screw fully. So and see, Google Health is doing great work in this field. They are trying to develop ways AI can help a surgeon uh, refine his or her technique. You see, there are not many surgeons in this world. I mean, and some of them are expert surgeons. By the time you are an expert surgeon, you are already 50, 60 years old. And you cannot use you have to use your time judiciously. Either you can operate on people or you can teach junior surgeons. So things like these, AI, can make a huge difference.
Yeah, in fact, it is already making a difference to places where there aren't as many doctors. So, for example, we built an application for detecting diabetic retinopathy, which is a very, very common disease. And it happens to millions of people around the world. So, but there aren't as many trained ophthalmologists. So now there is a system where you can take a picture using a cell phone, send it off to a server, and within minutes, the answer will come back whether this patient has this problem or not. And so a nurse or a compounder can operate this a clinic in a village and get the best possible diagnosis, which could save the eyes of so many people. So these are some of the examples where AI can help.
I work for a pacemaker company, and I can give you some specific examples where machine learning and AI is being used and how it's helping. So,
Alok, yeah, your talk will be scheduled shortly. So,
okay. But just very quickly, one area is in so pacemakers come with these home monitoring system where the function of the heart, you might be aware of the PQRST wave or the of the EKG. So that basically tells you how well your heart is working. And that data is being sent to servers constantly for those who have that home monitoring system turned on in their pacemakers. And obviously, no human has the ability to go through all these data in real time and to determine whether somebody is having a heart attack or somebody is having some kind of a ailment in the heart. So there are AI algorithms that are being employed to automatically detect if something has gone wrong with the EKG of a particular patient, and then it alerts the doctor, or in some cases sends the ambulance right to the person's home. So that's one area. The other one is in electronics manufacturing, which has to be extremely reliable, right? So when you're making a device like a pacemaker, you cannot go wrong. So previously, like 10 years ago, we used to have humans look at these manufactured devices to make sure that there was nothing anomalous in how they were built. Now we have cameras and machines that are looking at they make sure that there's nothing anomalous, like even a small amount of fiber that goes on the device that can cause leakage or electrical shorts that can create malfunctions in the electronics of the pacemaker or the defibrillator. So those are the two examples that come to my mind where the field of AI and machine learning are currently being used in the medical field.
Awesome. Yeah, I'll give another example actually where it's used in avionics field actually. X-51, that's the new supposedly supersonic aircraft made for like 30 people, and it's designed to not produce a sonic boom. And that was the main reason they say that the Concorde failed. And neural networks actually trained on a very small scale model in a windmill are used, and then they are scaled up. So I don't know the details of it, but right now it's being worked at Skunk Works at Lockheed Martin. Harsh, you should be interested in that.
I can only think of Renault's number when you're saying that.
Yeah, but it has a lot of applications, and the biggest thing actually I see specifically coming is the trust issue in the thing, and that's where the comment of gut came in a sense, like not inability to explain, especially in avionics and equally so regulated field like medical, where you should be able to explain each and every decision. And that is becoming a big problem, at least in avionics field.
Sanjay, you're right about the medical stuff as well. The FDA is going after a lot of manufacturers, including us. We submitted an FDA application, and they were very nervous about the AI use in the black box, and they don't trust that.
Yeah,
so that's a problem.
Yeah, and it's like a whole like DO 178C where you have to possibly execute each possible code and not come with a solution that is divergent, and that's causing actually a lot of problems. But X-51 is supposed to take its first flight very soon.
Yeah, so in the medical field, I think currently the way it's being used is, at least in the medical device industry, is to assist in making decisions, not in the final decisions. Right? So like, for example, again, in the pacemaker, the therapy that a patient receives, that's based on all the inputs. I mean, from the heart, and there are algorithms that go in that are not AI-based, that are more based on science and engineering, sound science and engineering, that can be explained to somebody, right? There's a rationale behind why a therapy is delivered to a patient, as opposed to just using an AI kind of an algorithm. But AI is being used to assist in that process, right?
I agree
where the issues are, so that fewer mistakes are made.
Yeah, no, look, I agree with you. That's the where it is being used and will have to be used. But I just tell you, I mean, just a recent experience. We submitted an FDA, and they came back with a bunch of questions about, are you using this? Are you using this? And showed significant nervousness of FDA if anybody claims that they're using AI because they think of that as a black box.
Yes. So
yeah, we're seeing the same problem with actually FAA also. I think the engineers at FAA are not up to date as like engineers in private industry. So then there is a mistrust there, and so it's same thing with FDA, I guess.
Okay, so we are at 2 hour 15-minute mark. Any other experts in the field who would like to chime in? And otherwise, we can give Vineet a break. I mean, but thank you so much, Vineet. I'm just amazed at your knowledge.
So thanks, Vineet. Yeah, Vishwa, just not an expert, but I want to just mention that that the person who's so when it comes to healthcare applications of AI, the person who's doing a really cool work that spans all the things that have been discussed or is Alpan. So his team is using AI for social good, and they also do healthcare kinds of use cases. But his challenges are amazing. See, at Kaiser, my team has access to very high quality data, tons of data, very high quality. But for Alpan, there is no EMR or anything like that. So they have data from the field, and it is very noisy. And they do telemedicine. They do all kinds of magic with this data. And his team has also won competitions in AI modeling, etc. So I think it'll be worth our while. I mean, it will be very inspirational also to hear Alpan describe what he and his team are doing.
By the way, I just want to point out that while Navdeep has access to lots of high quality data, he has more compute power than at his home than in his office.
It used to be true, but yeah, Kaiser works slowly at times, but now Kaiser has a lot more compute power than I do.
Our entire batch to have a GPU at his home, on his home computer to do machine learning.
I have, yeah.
And his wine cooler is always full.
Yes, but I've emptied it out.
Oh, come on, Navdeep.
Last 1 year.
So Navdeep, is Alpan back in our group or not? I know he had left.
So yes, he plans to come back once he gets some time off. So he's always very busy. He was in this talk. So
he was. Okay.
Yeah, he was.
Okay.
In fact, you can see a message from him saying signing off.
Oh, okay.
Yeah, there he is. Sorry, you have to drop off till 9:46.
Okay, hello, Sanjay and Harsh. I mean, anybody, Asad? कुछ जोकी मारो यार।
Yeah, Zed, कुछ याद आया?
सब कुछ भूल गए भैया।
अरे यार, कुछ तो सुनाओ।
आज सुनने का दिन है, सुनाने का नहीं।
ये कि वो पीछे रखा हुआ है, लेकिन ये मत सोचो कि चला गया सब कुछ।
नहीं, एक तुमने कहा था कि OHT से कुछ याद आया था तुम्हें, बहुत लंबा है, टाइप नहीं कर पाए।
क्या था वो? हाँ, उसको था नहीं, वो साहब वो बोले, बेटा आया, बोले भाई डैडी बताइए ताजमहल किसने बनाया था? बोले नहीं बेटा पता नहीं। फिर चला गया, फिर बोले नहीं डैडी बताइए पहले प्रधानमंत्री कौन थे भारत के? बोले बेटा पता नहीं। फिर बोला डैडी, बोले यार, बोले डैडी आपसे सवाल नहीं पूछेंगे। बोले अरे बेटा ऐसा मत करना, अगर सवाल नहीं पूछो नॉलेज कैसे बढ़ेगी? तो वैसे तो सवाल पूछने ऐसे ही हालत है हमारी आज।
All right, so shall I speak now?
Yeah. Hey, thanks, Vineet.
Thank you, Vineet.
Thank you.
Good to see everyone.
Thanks.
Yeah, this was a great question, Vineet. Thank you so much.
Thank you.
Yeah. Thanks everyone for attending. Bye.
I hope the level was okay.
Yeah, it was great.
Well, for you maybe it was okay, but maybe
but you can make a thing simple, but you can't make it simpler. So you have to do some calculus. You have to do dy dx to
yeah. I mentioned that. Yeah. I didn't get to the part where we were working on what our algorithms are like, the ones that I've been working on in the last year.
Yeah. So I saw that paper on the second order optimization.
Yeah.
So
that's doing very well now.
Yeah, I saw that. So I put it there. Actually, in our area, things have completely been taken over by neural nets. That's the speech recognition and text to speech, everything. So all the signal processing is kind of the same way. The computer vision guys, most of the old professors are in the same.
Right. Absolutely. Yeah.
Even noise cancellation for this. Like for video conferencing, if you want to do a good noise canceller, the neural net method is much better than any other method we had till now. It's actually it is more applied and it's working very well. Actually,
excellent. Yeah. That's great.
Yeah.
Very good.
Thanks.
Bye.
Yeah, so your presentation is available as a general thing, or
I can actually send it out. Where should I send it?
So should I just type here I will send it to Vishwa, so you can type Sandeep at
Vishwa, then you will post it wherever.
Yeah. You can send it to Vishwa.
Tie it to the talk.
Yeah. We can.
I got only to about 40% of the presentation, or 30 to 40%.
Yeah. So just send it. We will all learn, and then we will come back with some more questions.
Okay. Sounds good. I will send it to Vishwaranjan right away.
Okay. Thanks. Thank you.
Bye.
Yeah. Bye. Thank you. Hi, GK. अमित तुम लॉग ऑफ कर लो.